Hello, everybody. What we're doing today is having a look at some of the basics about waves. And let's start off by thinking, what is a wave? So I might say a wave is anything that oscillates. We might also say that a wave carries energy and information. And so then the waves that we kind of know about, well, water waves. So if the water waves are huge, we know there's been a storm in the Atlantic. The water waves are just ripples on the surface, then there's a light breeze across the lake. Then we've got sound waves. So sound waves, how you're able to listen to me now. So you can sense the information which I'm sending to you through the sounds that I'm making, and also the energy which is allowing your eardrums to vibrate. And then the other classic is light waves. So with light, you can see what I'm writing and so on. And actually, fundamentally, wave ideas go right to the heart of physics theory. Wave ideas explain the status of the electron around the nucleus of an atom, for instance. And we find that actually small particles can only be defined by a wave function, which is basically a mathematical equation that looks like it should be a wave. But that's jumping ahead. So that was our first number one. So let's go to number two. I'm going to draw a picture of a wave. So this is going to be tricky. Here it is, a picture of a wave. Try and get this quite neat. And I'm going to say, well, okay, it goes up to here and it goes down to here. And it's going to go. Don't. And first of all, what's on the y-axis? Well, the y-axis for a water wave could be height. And so 0 here at the center would be sea level or the level in the lake. And when the wave went by, the water height would go up and then down and then up again and then down. So it would go below the average and then above the average and below the average and so on. And what about if it was a sound wave? Well, if it's a sound wave, this could be pressure. So it's whatever it is that's oscillating. So for a sound wave, it would be pressure, and the 0 would be normal atmospheric pressure, and the pressure would go up to a maximum and then down below atmospheric and back up again, and so on. Then we'll take a look at the x-axis, and the x-axis we might have distance. But hang on a minute. Surely the picture of our water wave is going to change with time as well. Well, yes, this picture is a snapshot or a photo or a picture. It's a picture of the wave at a fixed instant in time. So what we've done is we've taken like a photograph of the wave, and that's what it looks like. And so there's two things that we can recognize on this picture. One of them, first of all, is the amplitude. The amplitude is just how big the wave is this way. And you'll notice that it's measured from the 0 point. It's not measured from the bottom to the top. I don't know why, but that's just a choice. And this is known as the amplitude. and it's given the letter A. It could be in meters if it was a water wave. It could be in pascals if it was a pressure wave, and so on. So that's the first thing that we can get from this picture. And then the second thing we can get from this picture is the length of one complete wave. So the length of one complete wave is from here to here, or it's from here to here, or indeed it's from here to here, whichever you like. It's the length of one complete wave. So I'm going to draw it here because it's easiest. And this is the wavelength, and this is definitely measured in meters. And I'm sorry to say it's given a Greek letter, which is called lambda, which, if you don't know it already, you're going to have to learn it. Sorry about that. So there it is. It's a lambda. It looks like an iPad being propped up by something just behind it. Okay, so that is a picture of our wave. But hang on a minute. Didn't we say that actually that was at a fixed instant in time, and actually the wave might be varying with time? So over here, I'm going to draw another picture. On the y-axis, I've got the same thing, height or pressure. And the pressure goes up and down the same amount. So I can draw these two dotted lines in again. And the pressure goes up from zero or ambient or atmospheric up to a height and back down again. But this time on the y-axis, I've got time. Distance was in meters. This time is in seconds. Okay, and then I'm going to draw it sort of deliberately different. But I don't really have to, because you know that this is now a time axis. So this is time ticking away, not distance. This is a graph of how the wave varies with time. And this time it's at a fixed location. So here I want you to imagine that instead of taking a photograph of some water waves, you're moored in a boat and you're measuring the height as time goes by. So you've got a stopwatch. You're moored in a boat and your boat's going up and down as the waves go backwards and forwards. So you've got a fixed location because you're anchored, but you've got a stopwatch. And this is a graph of how the height of the water wave varies with time. Now, the amplitude is just the same. But what does it mean now if we go from here to here? Or indeed from here to here. In the previous picture in green, this was the wave length. Now this is the wave time. In green, it was the length of one wave. This is the time for one wave. And this is given the letter capital T. So, wave time capital T is also known as the period. I don't know why. The period is the time for one wave. The time for one complete wave. So maybe I'll just go back into green again, and we'll say over here the wavelength. The wavelength, lambda. Lambda. I better spell it lambda. Isn't that funny, with an M, a B, and a D in the middle? It's a Greek letter. The wavelength is the length of one complete wave. And the wave time is the time for one complete wave. And you'll notice that you can't get the wave time off the graph on the left, and you can't get the wavelength off the graph on the right, even though they are related to each other. Which brings me on to the final part, which we're going to do in black. We know from sitting on the beach that waves move along. We know from listening to cricket matches that sound travels at a finite speed that's really quite slow. So finally, we have the wave equation. It's known as the wave equation. And the wave speed, well, like any formula for speed, the wave speed is distance over time. But we can say, well, suppose we take the distance, the wavelength. How long did it take to travel one complete wave? Well, it took one period. So in symbols, we get lambda over capital T. Capital T, you might say, what about capital T? Surely that's temperature. Well, I'm afraid it's also period. And we can check the units. What's wavelength measured in? Wavelength's measured in meters. What's period measured in? It's measured in seconds. What's speed measured in? It's measured in meters per second. Now, there's one last thing, but for reasons which I'm not quite clear about. When we talk about the wave time, we quite often talk about frequency as opposed to period. The period is the number of seconds per wave. The frequency is the number of waves per second. So that means we define number of waves per second. Well, hang on a minute. If one's the number of seconds per wave and the other's the number of waves per second, they must be related to each other. Suppose the period was half a second. Well, how many waves would there be per second? 2. 2 is 1 over a half. So I hope you can see that the frequency must be 1 over the period. So in symbols, frequency, I didn't mention the frequency is given the symbol little f, not big F, that's force. So frequency equals 1 over period. What about the units? Well, you can see that since 1 over period is 1 over seconds, then frequency is in 1 over seconds, which is true, but it has also got its own unit, which is the hertz, and its abbreviation. So finally, go away. Finally, I'm sorry, this has gone on longer than expected. The wave equation, therefore, is usually written wave speed equals frequency times wavelength. Is that the same as our previous one? Well, yes, it is, because if we look at the previous, wave speed is lambda over t, but f equals 1 over t. So if we want to divide by t, we've got to multiply by frequency. Also, we can say to ourselves, well, if the wavelength's 2 meters and we have 3 of them each second, then we're going to travel at 6 meters per second, because we're going to do 2 meters 3 times at 6 meters in a second. Okay, so that ends my little talk on the basics, and now you can get on with the rest of this worksheet. Thank you very much.